Hi, so there are basically two types of water turbine. There's the reaction type and the impulse type. The reaction type is the earliest type. It's the type that works off the mass of the water, the weight of the water. The impulse type was developed much later, and that's the one that works on water pressure, the pressure of the water hitting it. Now, a reaction type, or a very simple reaction type, is the undershot water wheel, where you basically take a wheel with some paddles and stick it in a river, and the mass of the river flows past the paddles, hitting the paddles and turning the wheel. Now, it's perhaps the least efficient. It's about 35–40% efficient or something like that. It is using the weight of the water, so it's much better if we put it over the wheel, let it drop into the wheel and let the gravity and the mass of that water turn that wheel, and that's called the overshot. Surprisingly enough, that's about 60–65% efficient, and so very much more efficient. So those early types of water wheel, the water wheel that were used for centuries. Then along came a guy called Pelton in 1870s, about 1876, 1878, something like that. And he thought that, okay, water has two properties. Yes, it has mass, but it also has pressure. You can get pressure of water by the head of the water. So if you have a column of water, the top of it is up here and you drill a hole in it, the water will spurt out. The water spurts out in relation to the mass of the water above it, creating a hydraulic pressure. The higher that is, the more force that spray will spray out with, because the pressure is greater. We can have a high head, a medium head, or a low head. Low head, obviously, there's not that much pressure, and that's the situation in a river. Rivers fall from a height to the sea, but they don't have that much difference in certain places between that point, and so the head is very low. But of course a river has a big volume of water when it gets into a situation like that. Just think of the Mississippi. And that mass of water is moving, and we can use that mass to turn a wheel. And that's why water wheels are predominant on lower stretches of river. They actually stuck them on boats as well and had something called boat mills. The problem with them is they broke the moorings and crashed into everything. But they were there using the mass of that water. So it's an ideal situation when you have a low head and a large flow to use something like an overhead wheel. Now, we're not in a situation like that. We're in a situation predominantly where we have a medium head created by the utility, or for the middle section of a river where the head is higher but the flow rate is lower because we're looking at tributaries. Then of course we have the situation where you might be in a mountain, and of course you've got the high mountain flowing down to the medium hills, and you've got high head and low flow because those are streamlets feeding into the rivers and streams. So we have these three distinct situations. Pelton wheels work best when it's high head and low flow because there's a lot of pressure there to be used, and Pelton wheels use pressure. So let's have a think about this situation. If we have a high head of water, we can use that head, force the water through a nozzle, and of course the volume of water we're using reduces dramatically, but the pressure increases tremendously, and we get a jet of water. If we force that jet onto something like that, then that is obviously going to spin. Now, in his early experiments, Pelton used pretty much what was an overshot wheel. It's just a wheel with some paddles, and he forced the jet at the paddle, and of course it turned it round, and it's going to do that. We know that. If we take a garden hose and point it at a bicycle, the bicycle wheel will spin, and pretty much the same thing was happening. But when that water hits, of course, it sprays out everywhere. What would be much better is if we could get that jet, turn it around and force that backwards to add to the forward motion. Of course we can do that, and that's exactly what Pelton did. We look at the shape of the Pelton wheel. The jet hits the centre point, is split into two, turns around, and then the jet continues forcing out, and that's why a Pelton wheel is so much more effective. Now, people have suggested using these things, spoons, for making Pelton wheels, and well, actually they don't work as a Pelton wheel because the jet hit here, it's not split, it splatters everywhere, and it comes forced out at an angle. So although it adds a tiny bit to the turning motion, nowhere near the same that turning that water completely around the Pelton bucket. Of course the Pelton wheel is brilliant, but it has its limitations. Well, it needs a high head. It's difficult control if you get head variation. It's expensive to manufacture because of the bucket shapes. It's prone to wearing out, and this advantage that it gets of efficiency decreases quickly over time. They also tend to be quite large and heavy, as this one is. And those disadvantages were recognised, and in about 1919 along came a guy called Turgo. Turgo looked at the Pelton and thought, yeah, that's a bit disadvantageous. What about if we cut it in half? And that is exactly what a Turgo turbine is. It's a Pelton turbine cut in half. Now, Pelton turbines work best if the jet is in that direction, directly parallel to the edge of the circle. Turgo turbines work best if the jet comes in somewhere between 20 and 30 degrees. Now, another issue with the Turgo turbine, with the Pelton turbines is, remember, the jet is coming out, being turned around. Well, of course, it's going to hit this one, which is problematic if you put these two close to each other, if you don't offset them, because that impulse is hitting the back here. With a Turgo turbine, the water comes in at 20 to 30 degrees, does its work, and then exits on the reverse side of it. So Turgo turbines have good efficiencies, around about 90-93% efficient, something like that. They're also appropriate for less technical builds. These things, unless you actually form that shape, so if you try using spoons, then you're not going to get a Pelton wheel, you're going to get what is basically an overshot wheel that you're spraying a jet at. These ones actually are much more capable of an easier DIY application. So if we take our spoons and we lay them over each other like that, spray the water onto there, then you have yourself a Turgo turbine. So it's possible to make Turgo turbines from spoons, not really possible to make a Pelton wheel from spoons. So Pelton wheels are difficult in their construction and therefore expensive, whereas Turgo turbines are much simpler in their construction and so cheaper. Now, of course, there are other kinds of turbines. There's the Francis turbine, for instance. But I just want to point out that turbines fall into those two camps. They're either an impulse type turbine or they're a reaction type turbine. On the reaction type turbine, you're using the mass of the water to turn the wheel. On the impulse turbine, using the pressure of the water to turn the wheel. Some lend themselves to different situations. So reaction turbines are great for low head, high flow, and impulse are great for high head, low flow. In something like a Pelton, you need that. In something like a Turgo, you can use a medium head and low flow to be able to generate. Anyway, I thought I would cover the differences between turbines, what families they fall into, and point out actually the Turgo turbine, because we are going to be building a Turgo turbine, hence the big pile of spoons. I hope you enjoyed this video. I hope it helped. Thank you very much for watching, and please do remember to like and subscribe.